Hello everybody, my name is Jose Antonio Martinez. In this tutorial, I'm going to talk about the implementation of automated sample extraction using pressurized liquid extraction. The first of all, I'm going to explain the basics of fundamental of pressurized liquid extraction, which from now on I'll refer to as PLE. PLE is a solid liquid extraction which use solvent extraction at high temperature and pressure, always below the respective critical points, so that the solvent remains liquid during the extraction process. As a result of using this pressure and temperature condition, a change in the physicochemical properties of the solvent occur. For example, mass transfer rates are improved, while at the same time the surface tension and viscosity of the solvent decrease, and the solubility of the analyte increase. This allows the solvent to penetrate more easily and more deeply into the solid matrix being extracted. As a result, significantly higher extraction yields are obtained compared to conventional extraction. There are two main work modes, static and dynamic. In static mode, the extraction solvent is not continuously replaced, but if more than one extraction cycle is used, the solvent is partially or completely replaced after a certain time. In the static extraction mode, an equilibrium can be established between the compounds that are still bound to the matrix and the liquid phase in which the analytes are already solubilized. Thus, the efficiency of the extraction procedure will not increase beyond this point, and degradation of some compounds and undesirable chemical reaction may occur more easily. Therefore, it is important to carefully optimize the static extraction time. The process of extracting analytes from semi-solid and solid sample can be described by the following 5 steps: moistening the sample with extraction solvent, desorption of compound from the matrix, solvation of the compound in the extraction solvent, dispersion of the compound out of the matrix, and diffusion through the nearest solvent layer around the matrix to finally reach the bulk solvent. The parameters to be carefully considered are temperature, extraction time, and pressure in order to relevance extraction efficiency. Temperature affects the physicochemical properties of the solvent. It affects the mass transfer properties, changing the surface tension, diffusivity, and viscosity of the solvent. In this sense, surface tension and viscosity decrease, while diffusivity increases with increasing solvent temperature. All these changes in solvent properties resulting from an increase in temperature allow for faster mass transfer and improve sample weighting. In addition, the desorption of the analyte from the matrix into the solvent is promoted at higher temperature, as the intermolecular interaction binding the analyte to the matrix are reduced. The extraction time in PLE is defined as the time during which the solvent is in contact with the matrix at the desired pressure, temperature, and flow rate. The extraction time required to completely extract a particular matrix will depend on the matrix, the type of compound, and the extraction mode, being the most critical of all. PLE can be performed in continuous flow or in static mode. Different instrument designs are required for each mode. Pressure has a limit impact on solvent characteristics as long as the solvent remains liquid. Higher pressure means better wetting of the sample, resulting in better extraction efficiency, and generally a pressure of 50 to 150 atmosphere is used. In some cases less, unless the solvent saturation pressure is used. The use of dispersants such as glass bead and diatomaceous earth is sometimes common to promote uniform distribution for extraction yield. Moisture content can also affect extraction yield. The presence of water can compete with the extraction solvent and decrease the extraction rating. Now let's talk about method validation focus on unique matrices, an automated approach for green coffee and tea using liquid chromatography coupled to mass spectrometry. This slide shows the extraction parameters of the method. The preparation of the extraction cell is as indicated. First, weigh 3 grams of sample and hydrate with 3 milliliters of water for 5 minutes. Mix the hydrate sample with 3 grams of diatomaceous earth and place a cellulose filter in the bottom of the cell. Weigh 225 milligrams of magnesium sulfate. Add the sample, stroke diatomaceous earth mixture, and finally close the cell correctly. The extraction cell is then introduced into the system and the extraction starts. Once the extraction is complete, the collected 10 milliliter extract is transferred to a 15 milliliters Falcon tube. In the case of coffee, a freezing out step is applied to precipitate the lipid content. Subsequently, the extract is centrifuged and injection vials are prepared as shown above. As a result, 0.04 gram sample per milliliters of extract is injected in the LC-MS system. This slide shows the parameters of both the liquid chromatograph and the mass spectrometer, in this case a triple quadruple. The strategy for quantifying our results, procedural standard used for method validation, and matrix match calibration used to calculate matrix effects. In green coffee, parameters such as linearity, repeatability, recovery, and reproducibility have been evaluated for validation. At 3 concentration level are 0.01, 0.02, and 0.05 mg per kilogram, and 233 compounds have been validated, obtaining 89% of the compounds at 0.01 mg per kilogram as LOQ. The remaining 11% at 0.02 mg per kilogram is shown above in yellow. The matrix effect on green coffee has been assessed and found to be medium to low for 86% of the compounds evaluated. The remaining 14% show a high matrix effect, mainly suppression. Compounds eluting at minute 4, such as thiamethoxam and flonicamide, have a high suppression due to the coelution of caffeine in the same retention time. The same validation criteria have been evaluated for black tea as for coffee. 228 compounds have been validated, of which 90% at a LOQ of 0.01 mg per kilogram, the remaining 10% at 0.02 mg per kilogram. In the case of black tea, the matrix effect is medium to high for 78% of the compounds, while 21% show a low matrix effect. In the case of tea, more interference and suppression are observed than in green coffee. Finally, the importance of a hydration step in the extraction to extract compounds with higher polarity has been assessed. Analyzing the PT sample, it has been observed that without the hydration step, compounds such as acetamiprid, dimethoate, imidacloprid, proposure, and thiamethoxam are only half recovered. In conclusion, PLE is a good alternative to the Quecher's methodology for the analysis of complex matrices. The addition of water is necessary to extract the more polar pesticides. In the case of green coffee, as in tea, caffeine causes suppression during elution of compounds with common retention time. This is the reference. And finally, thank you for your attention.